We discussed about online bid, right? It is one of the use of hash function, where we have studied Alice, Bob, Chan. They placed their bids. They didn't directly place their bid over online. They first share the hash function of their bid, right? Once it is posted online, after that they submitted their bids, right? And later it is revealed. So whoever uh, what the highest bidder win this online bidding, isn't it? So here we can't change the bid after hash value is sent over online. So that is one advantage if you use hash function for online auction or online bid. So we'll move to the next use of this hash function, that is, am I audible? Am I audible, right? Yes. Am I audible, guys? Anyone, please?
Yes,
Yes,
ma'am, you're
ma'am,
audible.
you're audible, ma'am.
Okay, okay. Huh. So the next use of this hash function is spam detection. Before starting how it is done, let's see what actually the spam is. What is spam? We in day-to-day life in our mail we find lots of spam mails, right, in our spam box, isn't it? So what is spam here? Actually, it is irrelevant, or you can say unsolicited messages which is sent over internet to number of users, right? So it may be because for the purpose of advertising their product or their property or whatever, or they may also send spam messages for phishing, or you can say spreading malware, so that you can open the particular mail, they can get the access to your system, and they can cheat you, right? They can steal all the information that you have stored in your cell phone, or you can say in your system, isn't it? So obviously none of us want to see the spam messages in our mail, isn't it? So this hash function is used to reduce such spam messages. Okay, so one method followed here is, consider Alice, she accepts the email, okay, from any sender only. They have they have created a mail using a work. That means if they have spent enough system resources using that, if they have created the email, then she will accept it. Now the question is, how do you measure the so and so person who are sending the message or the mail to her, using her system resources? So how do you verify it? Well, she look into the CPU cycles that are used to create the actual mail that was supposed to send by the another sender to the Alice. So if this method is followed, it can limit only the amount of email that can be sent, okay, but it will not eliminate the spam. Okay, so you can conclude here looking at these points that if enough work or the resource of a system is used to create a mail, then that mail will be accepted. Okay, so if this method is followed, it can limit the amount of email that a particular sender can send particular mail to the Alice, but it will not eliminate the spam. Okay, how it reduces or the limit the amount of email that can be sent? Because if the CPU cycles are used more, obviously the person who is creating a mail, it costs a lot for him to create such mails, right? So that's why sure that if a particular message need to be sent to a million users, then obviously if it is costing more to him, then obviously he'll limit himself to sending such mails, isn't it? So if this method is followed, this will not eliminate the spam. Okay, now what can be done to reduce the spam that we are receiving? There is a method where the hash function is used. Let's consider this. Okay, So let M be the email. I mean, email message that wants to be sent. And there is letter T also here, which treat it as a current time. I mean, I'm sending a mail, so the timestamp is given to that mail. So that is represented with the letter T, and this stands for current time. Okay. Now, the message, whatever message here M is there, this includes the sender and the intended recipient's email addresses. Okay, the sender sends, I mean, the sender who wants to send this message, that is, the sender of message M, must determine the value of R here. Now, what is the, here he has to find out the value of R. Like how he has to determine this value R. See, you can see in the next point here. Okay, so here, uh, when the sender, when he wants to find the value of R, you can see in this line, yes, perform hash function on M and R and T so that, okay, it has, I mean, whatever output that will get for this function, I mean, after performing hash function on these values, here the first n output bits must be 0 and then some other value. Okay, so to get this output, you should, I mean, sender should find the value of R here. He has to find in such a way that the first n output bits must be 0 when you apply hash function on this. So hash function, you have to apply it on message M, and the R value, randomly you can select R value and the current stamp, that is time. So when you apply hash on this, the output of this hash function should be, n output bit should be 0 and then followed by some value. Okay, so as you can see, n bits of hash value are all 0 here. I hope this is clear now. So once this is done, once this calculation is done, the sender sends the triple here, MRT. The sender sends this triple, that is MRT. Now, before Alice, that means the recipient, accepts the email, she needs to verify that the time, whatever T is present here, that is resent. And after performing hash function on these, begins with N0. Okay, so now whatever the recipient who accepts the mail which is sent by the sender, say Alice, so here, after performing hash function on these three, the output should begin with N0. In this way, the what receiver can confirm this is the what intended mail that I'm supposed to receive from the sender. Okay, so after performing all this calculation, what is the work at the sender side and the recipient side? I mean, how much work or the resource used at the sender side? You can see here at the sender side, he has to perform average of 2 power of n hashes. He has to perform 2 power of n hashes here. Why? Because he has to find the value of R, right? So that the output of hash function on this should have n zeros. It should begin with n zeros. That's why on an average of 2 power of n hashes should be done at the sender side. Whereas work for the recipient, and that means the one who receives the mail, he has to perform only one hash function. That is, he has to perform hash function on this only one time, because he need not to find R value or M value or T value here, right? He just has to perform hash function on this received MRT. Okay, so that is how you can reduce the spam. Here you can see the sender works increases exponentially in n, whereas here with respect to recipient, there is a small calculation is required regardless of the n size. That is one more thing. And here, to reduce the spam, obviously, work level is acceptable for normal email users. So you have to set a work level so that that is acceptable for the normal email users. Okay, and work level should be unexpectedly high for the spammers. So the one who generates the spam has to, the work level has to be set as high, so that spammers should not be able to generate the mail and should send it to the for the intent receiver. Okay, so that is how the spam reduction is done with the help of hash function. Am I clear to everyone? Are you all following this?
Yes, ma'am.
Yes. Yes. Are you following this? Please
Yes,
reply.
ma'am.
Okay, so those are the two uses of hash function. One is online bidding, the next one is spam reduction. Okay, next we'll move on to the next topic, that is visual cryptography. So till now we saw like message digest was used, secure hash function was used, and tiger hash function are used, and many other hash functions are used to generate, I mean, in the cryptography, right? So there is another form of secret sharing, that is with the help of visual cryptography, or you can say it is a visual cryptography. Okay, in this we will study Alice and Bob. I mean, two users will share an image. I mean, there is one image. Okay, this is divided. Okay, a share, one share is with Alice and another share is with Bob. Okay, so what, when you overlay these two share, then you can find out what actually this image is all about as a whole. Okay, so the thing is, now this Alice will not reveal her image, and Bob will not reveal the image which he is having now. Okay, so now consider there is an attacker who tries to find out the image that is with Alice. Since she has a share of this image, okay, so even though intruder hacks her image, he'll not be I mean, he'll not be knowing what actually the information is present in the image. The same goes with the Bob share as well. So to find out what is present in the image, both shares are required. Okay, now the question is it possible? We'll see in the next slide here. Okay, so consider this example, which is an example for visual cryptography. Here you can see there is a see, this is a pixel. Okay, here the share 1 and share 2, I mean, this pixel is made as share 1, I mean, divided, and there are two share of this pixel, that is share 1 and share 2. When you overlay these two shares, then you will be obtained with the final image. So let's see this. In this, as I said, it is splitted and made it as a two share. One, consider this share goes with Alice and the next share goes with Bob. When you put it together, then you can see a actual image. Okay, so here, if now consider the pixel, maybe will consider the image. Let assume it is a black and white image. Okay, so we have to deal with the white pixel as well as black pixel here. Fine. So let's start with the white pixel here. Now just consider this is a white pixel, and you can flip a coin to decide whether to use row A and B. See, there are two output possible here. You can see this is a different output and this is different. Okay, so we'll see both the possible now. Okay, so here Alice gets share 1 here, as I said. Where is the cursor? Huh. So this is Alice share. Okay, this is selected from the row A, and Bob's will get this share. I mean, Bob will get this share too. Okay, when you overlay this together, you will be ended with this image. Okay, what if other case? This is the Alice share and this is the Bob share. then what happens? The output image will be in this form. I mean, when you overlay this, you can get the final image of it with respect to white pixels. Now what happens with the black pixel? You can see here again it is splitted as two share, this share 1 and share 2. When you overlay this, you can see again the complete black pixel, right? Yes or no? If you go with another case, that is D here, the share is different here compared to C. When you overlay these two, again the output image will be black here, isn't it? Yes. So the thing is here, you have to remember, uh, when you overlay the share images, then only you will be ended with the final image. So this is used in visual cryptography if a black and white image is involved. Fine. So let's see this example. Okay, that is what here. Let's consider this is Alice share. Okay, there is one image where this image is splitted as this one share that belongs to Alice, and the next part or the next split uh, is with Bob, and this is Bob share. Okay, when you overlay these two images, then you will be ended with the final image. That is, you can see a girl here, right? This you will get it only when you merge these two. Okay, in this way the visual cryptography was used to share the information in initial days, apart from following other encryption and decryption techniques we have studied so far. Okay, this is one example under visual cryptography. Now let's compare the cryptography methods we studied in first module, and also you started in the previous semester. Now the thing is, can you compare visual crypto with the regular crypto? In regular crypto we need keys, right? With respect to symmetric key, you need key. With respect to public key cryptography, you need a pair of key, private key and public key, isn't it? In the same way, there we need keys to perform encryption as well as decryption, whereas here in the visual cryptography, we are not using any key, or you can say the shares that belongs to both the users, both the participants can have. I mean, those who have the images, they play as a key here. We can treat their shares as a key with respect to visual cryptography. Now, with the encryption method, I mean, with respect to regular encryption, if a attacker performs exhaustive key search, then obviously the encryption algorithm can be known to the attacker, right? Except for one-time patch. So this is what we discussed in first module. With respect to visual cryptography, what happens? Exhaustive search is not possible at all. Fine. So this is the difference between regular cryptography and the visual cryptography. I hope I am clear to everyone. So we'll move to the next part, that deals with the random numbers. Now, what is random numbers? You all might be knowing, right? You have studied cryptography in the last semester where you make use of keys, and these keys are randomly generated, right? So random numbers are what? While generating the numbers, regular pattern is not followed, right? So we have in Excel, we have random function. In Java coding, you have random function. In Python, you have random function, right? So when you execute that function at this point of time, you will get one number. When you execute the same function after 1 hour, you will get another value. It will not be the same one which you got in the previous execution, isn't it? So a regular pattern is not followed to generate the random numbers. We'll see how it is used in the cryptography. Okay. Now, as I said, random numbers are used to generate keys, right? So whatever keys we use in the symmetric keys, sorry, symmetric cryptography, as well as in RA, as well as in Diffie-Hellman, where we are using secret values. So those are all, those keys are all generated with those keys are all random numbers. Okay. So apart from this, we use random numbers in simulation as well. Simulation, it may be any simulation, maybe in MATLAB or network simulation, any other. Wherever you are using simulation, there we need values to try, right? We need to see the output for different trials for a particular approach. Then the random values are required. So there also you can make, this is one of the application, as well as in statistics. There also we consider the random numbers. Then consider, as I said, whatever the random numbers that we use in a cryptography, that must be statistically random and it should be unpredictable. So random numbers, those which we use it, that should not be predictable. It should be always unpredictable for the attackers or for anyone. Okay. So now let's consider an example or a scenario where there is a server which generates symmetric keys. The server which generates symmetric keys for the users. Let's see, there are 4 users: Alice, Bob, Charlie, and Dave. Okay, these are the 4 users who uses symmetric keys for the encryption purpose. Consider this. Okay, and symmetric key for the Alice is KA, for Bob it's KB, for Charlie it's KC, and for Dave it's KD. Now, what happens that this Alice, Bob, and Charlie together, these 3 people doesn't like this Dave. Okay, so they want to know what is the key that is given for this day. Okay, so what they will do, they'll gather all the keys that is provided for Alice, Bob, and Charlie. I mean, they pull these information together, KA, KB, and KC, and they'll find out, is there any pattern followed to generate these keys? Is there any pattern followed to generate these keys from the from the server, right? So if they find out there is a pattern while generating these key, then obviously they'll end with the key that is generated for the day. I mean, they will know what is the key generated for this day. Okay, so if this is the case, then you can say this cryptography function is compromised, right? If key is known to someone, then obviously the crypto system is compromised, isn't it? So that is one thing. So compromised. Oh, it's wrong. Okay, just remember, I'm not able to write in this mouse. So if that is the case, then this crypto system is compromised. So that is what I explained in this slide. Fine. I hope I'm clear till this point. So that is all about, I mean, the introduction about the random numbers. Let's see, let's see a real world example where random numbers are used, but while generating random numbers, they followed the predictable pattern. I mean, they could predict what random numbers are used in their uh, what to say, in their system. Okay, consider this example where you can see here non-random random numbers. The topic is given as non-random random numbers. To say random numbers are used in this example, but actually those random numbers are non-random. That means random numbers can be predicted in this example. So let's start with this example. As I said, it's a real world example, okay, where you can see the wrong way to generate the random numbers. Okay, so this ASF, what is the cursor? There is a company called ASF Software Inc. Okay, this organization developed an online version of poker game. that is in the name of Texas Hold'em poker. You might be knowing how, like, what is poker, how it is played, isn't it? Actually, I have no idea about this poker game. For the explanation part, I have gone through to some extent. Okay, so poker, obviously, it's a card game, right? Yes. Let's see where they went wrong in using random numbers. So in this game, as I said, in this poker game, the rules goes like this. So each player, I mean, for this game, there may be 2 to 10 players. Okay. So minimum two should be there. Maximum they have considered till 10 players for this game. Okay. So each player in this game, uh, what happens? First dealt with 2 cards face down. So each player will be having 2 cards, okay, in his hand, and their faces should be down. It should not be shown to any users who are playing, who are involved in this play. Okay, and then what happens? Then a round of betting takes place. So obviously, it's a gambling, right? So the round of betting takes place, wherein it is followed with, you can see here, 3 community cards are used, and this dealt with face up. That means these three is called as community cards, and this can be, I mean, these faces are up. That means what? All players who are involved in this play can see this community card and use them in hand. So they can use these cards. Next, after another round of betting happens, okay, after that betting, one more community card is revealed. You can see in this pic here, where numbered it as 3. So one more community card is revealed, and then another round of betting will happen. Finally, at the end, a final community card is dealt, after which the betting can occur. So initially what happens? The player will be having 2 card here, and it should be kept as secret. And then betting happens. 3 community card will be shown to all the players, and it can be used by the players. After again betting happens, then one more card will be revealed, that is shown to everyone, I mean all players in the play. And at the last, the final betting happens, where one more card is shown to everyone. So at the end, the winner, I mean, the winner of this play, the winner is the one who can make the best poker hand from his 2 cards, that is this 2 cards together with the 5 community cards. So those who have the proper match, then he will be the winner at the end. Now the question is, what went wrong, or where do we use this random number, right? See, it's an online. See, if you are playing physically, I mean, with everyone, obviously you will shuffle the cards that is there in the pack, and you will serve all the players, right? But since it is an online version, the random numbers are required. These random numbers are required to shuffle the virtual deck of cards. So while serving the players, obviously the shuffle has to be done between the cards, right? So to do that, the random numbers are used. Okay. Now this ASF software, ASF who developed the software to generate this random number had a serious flaw. So where, the serious flaw, that random numbers which were used to shuffle the deck of cards. So what happens as a result? Obviously, this program did not produce a truly random shuffle, and it was possible for the player to determine the entire deck in real time. Obviously, if there is a flaw, obviously there will be someone to find out uh, the required data from them, right? In the same way here, the player can determine the entire deck in real time. I mean, what are the cards that are going to show up, and what card each player may have with them because of this flaw. Let's see that Actually, so as you know, in a set of card, I mean in a deck, there will be 52 cards, right? So what are the possible shuffles? Obviously 52 factorial, isn't it? Which is greater than 2 power of 225 possible shuffles. So out of 52 card deck, you can shuffle 52 factorial times. So this AFS poker program use a random 32-bit integer. So this poker AFS poker software used a program which used a random 32-bit integer to determine the shuffle. So obviously, if this is the this many bit integer is used, then obviously how many shuffles can occur here are possible? Obviously, 2 power of 32 distinct shuffles could occur since they are using this bit integer for the random number generation. So to implement this, they used Pascal pseudo random number generator. So to do this, to generate this distinct shuffle, they used PRNG, which is Pascal pseudo random number generator, where the randomized function is used to generate the random numbers. That means 2 power of 32 distinct shuffles. Okay. Now, see, to start any what pseudo random number generator, you need a seed value. Seed value is nothing but the initial value. Okay, initial value or a seed value for this generation, for this generator was function of number of milliseconds since midnight. So this milliseconds of, I mean function of, the function is applied on number of milliseconds since midnight. For this, they for what this value is treated as seed for this generator. Okay, so since it is followed, you should know what is the total milliseconds for a day. So what is total milliseconds for a day? How many hours in a day? Sorry, 24 into 60 minutes into 60 seconds into, since we have to present it in milliseconds, right, into 1000. Okay, so the whatever value that we get here is less than 2 power of 27. So that's why I've written here less than 2 power of 27 milliseconds in a day. Then obviously the possible shuffles will be less than 2 power of 27 only. So if the attacker has or a player has all this information, then obviously it will be easy for him to find out uh, the cards that I mean it is possible for him to determine the entire deck in real time. So let's see that. As I said, the seed for this is milliseconds since the midnight. Each time to make a shuffle reseeded for this generator. Okay, so first seed is what? The millisecond since the midnight. So each and every time you want to shuffle, you have to reseed this generator. Now what attacker or a player will do, he will synchronize his clock with the server. Okay, what he will do, he'll synchronize his clock with the server. So the number of shuffles that need to be tested is lesser than 2 power of 18. When he synchronize his clock with the server, the shuffles that he need to be tested is lesser than 2 power of 18. So see, you can see from the previous slide, initially these many shuffles were possible, right? Later it is reduced to 2 power of 32. Later it is reduced to 2 power of 27, isn't it? Now, since he synchronized his clock with the server, now he has to test only 2 power of 18 shuffles in real time. So he will test each possible shuffle against up cards. Up cards means what? The community cards. Okay. When his calculation is done, then attacker knows every card after the first of 5 rounds of betting. So in this way, after performing so many tests, he may find out what are the cards with each and every player who are involved in this play or who are participating in this play. So obviously what happens here, there is a what to say, whatever random numbers that are used in this poker program is known to the player, right? Using this opportunity, always he may win the game. So that is what the point is here. So for what purpose they have designed to make a money out of this poker program, right? But that has failed here. Instead of that, they lost all the money to the player who know the flaw of this program. So that is what is all about the poker example, where the random numbers used are not truly random. Okay. So but here crypto random sequence are not protected. Actually, if truly random numbers are not used in any of the encryption program, then obviously there is a failure of using such algorithms in day-to-day life, right? For example, key string that is used for RC4 cipher, it follows the true random sequence. Okay, but for the generator, where the seed value you have to give is always an issue. Selecting the seed value is always an issue with respect to the generator, which generates random numbers. Okay, so that's all about random numbers. The next part we'll see in the next class. I mean, what is random from here? Last one topic will be left out, that we'll see it in the next class. So, any doubts? Yes? One second. Let me stop the presentation. Any doubts? Let me know.
No, ma'am.